dear students. In today's class, I am starting a new chapter, that is nuclear fission and nuclear fusion reaction, which is the sources of energy. The first topic is nuclear fission reaction. Now, in 1939, two German scientists, Hahn and Strassmann, observed that when uranium 92 was hit by a neutron, it split into two radioactive nuclei. One was barium and other one was krypton. Two other scientists, Mittner and French, named this as nuclear fission reaction. Now, in nuclear fission reaction, it is a process in which heavy nucleus such as uranium, after capturing a thermal neutron, splits up into two lighter nuclei of comparable masses. These products are known as fission fragment. The process is accompanied by the release of few fast-moving neutrons. Not only barium and krypton, neutron was also released in this process. And a huge amount of energy. With this, energy is also released, which is very large. The form of kinetic energy of the fission fragments and of the released neutrons, gamma ray, etc. This gamma rays was also released. So, when a uranium is hit with the neutron, the neutron is being captured by the uranium, and in turn, barium krypton is released with a lot of neutron with energy and gamma ray. So nuclear fission is the basis of nuclear bomb and nuclear reactor. So same type of reaction happens inside the nuclear bomb and nuclear reactor also. Now, fission of uranium 92 and 235 nucleus. Natural uranium, which occurs in the nature, is a mixture of two isotopes. So uranium is a mixture of two isotopes. One is uranium 238 and other one is uranium 235. These are isotopes which have different masses but same atomic number. Now, these are found in the nature in the ratio of 1:45:1. The isotope of uranium, this isotope, that is 238, can be fissioned only by fast neutron. Only the neutron is, if the neutron is very fast, then only it can break this isotope of uranium, and which has got energy which is above 1 mega electron volt, while uranium 235 can be fissioned by slow or even thermal neutrons also. Thus, when a slow neutron hits uranium 235, if a slow neutron hits uranium 235, it is captured by the nucleus and a new isotope is formed. So I'll just write the reaction. If uranium 235 is hit by a neutron, then a new isotope of uranium is formed, that is 236. It is formed. This new isotope, being highly unstable, at once breaks up into two fragments with the emission of 2 or 3 fast-moving neutron. It releases 2 or 3 fast-moving neutron plus energy and isotopes of barium and krypton. So, barium krypton, this is 56, barium and krypton with 3 neutron plus Q is energy, a lot of amount of energy is released. This is one of the typical fission reaction. In general, the fission fragments are found to be radioactive isotopes of elements lying in the mass number ranging from 70 to 80. So these are radioactive isotopes having mass number in between 70 to 160. All fragments undergoing several beta decay until they reach some stable end product. So this will continue having decay until and unless it reaches a stable element. So this is a nuclear fission reaction. Now, energy released in nuclear fission reaction. The binding energy per nucleon of nuclei of intermediate masses is greater than that of the heavy nuclei by about 1 mega electron volt. The binding energy per nucleon we have already studied in the previous chapter. Hence, fission of heavy nucleus into two lighter nuclei is bound to release a large amount of energy, that is Q. This energy release is the most striking aspect of nuclear fission reaction. So this energy is what is being utilized in nuclear reactors. So the rough amount of energy can be estimated using the binding energy curve. Now, according to the calculation of this nuclear fission reaction, the whole amount of calculation is actually not required. I will just give you the value of energy released. Okay. So if the nuclei of an uranium gets released and if it's converted into energy, then the amount of energy liberated will be 8.2 into 10 to the power 10 Joule. Okay, this amount of energy will be liberated. Now, the calculation of this is given in the book also. You can go through the book, but the calculation is actually not required according to the syllabus. Okay, only the reactions of this nuclear fission and nuclear fusion is required. The next which we are going to discuss is chain reaction in nuclear fission. I've already told you when a uranium nucleus is hit by a slow neutron, the nucleus splits. Okay, uranium, when it is hit by a slow neutron, then it splits into two nearly equal fragments having same number of masses, that is barium and krypton. Under favorable conditions, the emitted neutron fission other nearby uranium nuclei in the same manner, causing further emission of energy and more neutrons. So in this reaction, more number of neutron is released. Okay, more number of neutron is released. Suppose if a slow neutron hits one uranium atom, then it releases 3 slow moving neutron. And again this neutron will hit atom of uraniums. Okay, it will hit uranium, and again from each uranium, barium, krypton along with 3 neutron is released. Okay, in every reaction, the reaction is being multiplied. Okay, the reaction is being multiplied and a lot of amount of neutron is being released, and this neutron, one single neutron will release 3 more neutron. So a chain of nuclear fission is established which continues until whole of the uranium is consumed. This process is known as nuclear chain reaction. Since in the chain reaction, the number of nuclei undergoing fission increases by very fast and about 200 mega electron volt energy is emitted per fission. The energy produced takes a tremendous magnitude very soon. So this is uncontrollable type of a nuclear reaction. Now there are difficulties in maintenance of chain reaction, and the difficulty in removing them are also there. So there are 2 main difficulties in maintaining a chain reaction in natural uranium. First difficulty is the neutron emitted in the fission carry an energy of amount. A neutron carries an energy of amount 2 mega electron volt. Such fast neutrons have a much larger probability of getting scattered by uranium-238. So uranium-238 gives this type of neutron which releases 2 mega electron volt of energy. In this process, the energy is reduced by 1 mega electron volt and then they are absorbed by uranium-239 without fission. Now there is another isotope, that is uranium-235. Nuclei can however be fissioned by this fast moving neutrons, but their number in uranium is significantly small. So uranium-235 is very small in naturally occurred uranium. Thus, the neutron emitted in the fission of natural uranium are not able to continue the chain reaction. So the uranium which are released in the uranium-238 reaction are not able to continue the chain reaction because the energy is very less. This difficulty can be overcome by slowing down the emitted neutrons to thermal energies. So first of all, the neutron emitted by this type of uranium, the energy of the neutron has to be decreased and made it 0.03 electron volt. Then the probability of their absorption by uranium-238 would become very low, while the probability of their fissioning uranium-235 would become very high. Then it can easily fission this type of uranium. This job is done by moderators. There are moderators in uranium reactors, in nuclear reactors, which does the job of slowing down the neutron, which reduces the speed of neutrons rapidly. Thus, by placing moderators in the path of neutrons, the chain reaction can be maintained in natural uranium in spite of very small concentration of uranium-235. Now, graphite and heavy water are very good moderators. Now, the second difficulty in the maintenance of chain reaction is that fast neutron liberated by the fission of natural uranium travel a distance of 10 centimeter in a substance. If it is a uranium, then it travels a distance of 10 centimeter before they are slowed down and fission other nuclei. Before they are slowed down, they travel this much amount of distance. If the uranium block to be fissioned is of small size, then most of the neutron will move out of the box before they can fission any nucleus and the chain reaction will be stopped. Therefore, to continue the chain reaction, the size of fissionable substance could be bigger than a certain critical size. So the uranium material which is being fissioned has to be a favorable size, which is known as the critical size. Then only the fast moving neutron will be inside the uranium until it is being fissioned, or else the fast moving neutron will pass by the uranium and the uranium will not be able to be fissioned if the size is small. So it has to have a size which is known as critical size of the uranium. Now, the critical size of the uranium, suppose the radius of the uranium is R. So this should be greater than 1 by K. Okay. The value 1 by K is known as critical size of the substance. The mass of the substance of critical size is called the critical mass of the substance. If the size of the substance, this critical size is less than the critical substance is less than the critical size, then the chain reaction will not happen, because there is a critical size which has to be kept in mind if you are using any sort of radioactive substances. So when in a nuclear reactor, uranium are kept in a form of small balls. Uranium and other radioactive elements are kept in a form of balls, which is of favorable size or which passes the criteria of this critical size. Now, with this, nuclear fission reaction are of two types. Number one is uncontrolled chain reaction. If more than one number of neutron is emitted in a particular fission, cause further fissions, then the number of fissions increases rapidly with time. In the previous case, I've shown you one diagram over here. I'll show you the diagram. In this situation, there are more than one number of neutrons being fissioned. So if this more than one number of neutrons are being released, then the reaction is uncontrolled chain reaction. So this releases a very heavy amount of energy and it takes a tremendous magnitude within a very short period of time. This happens in nuclear bomb. So in a nuclear bomb, there is uncontrolled chain reaction. Now the second type of nuclear reaction is controlled chain reaction. If by some means the reaction is controlled in such a way that only one neutron of the emitted is fission causes another fission, then the fission rate remains constant and the energy is released steadily. Such a chain reaction is called a controlled reaction and it happens inside nuclear reactor. So suppose if in this diagram, suppose over here, if this uranium over here releases only one neutron, if it releases only one neutron, then it will hit only one uranium. So this doesn't happen. And if it releases only one neutron, then it will hit another uranium. So only one uranium will be hit and fissioned in every step. So this is a controlled chain reaction which happens in a nuclear reactor. Now there is a difference between radioactive decay and nuclear fission. Nuclear fission, the first difference is radioactive decay is a spontaneous process where nuclear fission is not. In fission, heavy nuclei are bombarded by neutron. Radioactive decay doesn't need any neutron, it happens by itself, whereas nuclear fission, a neutron is required. That is the first one. There is a topic difference between radioactive decay and nuclear fission. You can go through by yourself, at least 3 points, just note it down. Okay, with this I'll move on to another topic, that is nuclear reactor.